shall see one important question. Describe the characteristic of queuing system. This is important question. The basic characteristics of a queuing system are: first one, arrival pattern that follows Poisson process; second one, service pattern of servers that follows exponential distribution; and next one, number of service channels, that is C; and system capacity, whether it is finite or infinite; and queuing discipline, whether it is FIFO or LIFO or CSIRO or priority in random selection, like that. So these 5 components are very important to describe the characteristic of a queuing system. First, let us define arrival pattern. What is arrival pattern? This arrival pattern is measured by the arrival rate or inter-arrival time. Here we assume that the arrival pattern is to be Poisson process and it is noted as lambda. That's all. So arrival rate is always noted by lambda and it follows Poisson process. Later we shall see what is Poisson process. At present you observe the notations and terminology and basic definitions. And next, service rate. What is service rate? Service rate is nothing but service time distribution that is assumed to be exponential distribution, and mean service rate is usually denoted by mu. So service rate always denoted by mu and it follows exponential distribution. That is another important thing. And next, number of service channels. Number of service channel means number of how many counters, service counters are there, how many servers are there. So it defines number of servers, number of service counters, like that. So to provide service, we may have one or more counters or one or more servers. Okay. And it is usually denoted by C as per Kendall's notation. And next is system capacity. The system capacity, if number of persons are very limited and this only the number of person can be served today and tomorrow the rest will be served. So here today's number of customers has been restricted. For this case this is infinite. Any number of customers can be allowed to join in the queue, that is the system capacity is said to be infinite. Here the limited waiting space in some queuing process, so that when the queue becomes large. Further, customers cannot be allowed to join the queue. Okay. For this case, the queue is nothing but a finite queue. If there is if any number of customers are allowed to join in the queue, then the capacity of the system is infinite. So system capacity, in this fourth point, we are dealing whether the system is finite or infinite. Whether the number of customers or any number of customers can join in the queue or limited number of customers can only join in the queue. This process is dealt in the point system capacity. And next, fourth point is queue discipline. As we have already seen it, this is nothing but by using Kendall's notation. First one, M1 infinity bar FIFO. First M is Poisson arrival, Markovian or Poisson arrival, and second M is same Markovian model and service rate distribution, and that one is nothing but number of servers, that is 1. And here you see this infinity is number of customers there. So here it is noted as infinity. So infinite number of customers can be joined in the queue under the queue discipline FIFO. I mean first in first out. Similarly, the same rest of the queuing discipline can be defined. MMC means same Markovian model, and number of servers is certain number of servers are there. So C equal to 10 means number of servers are 10. C equal to 1 means it goes to first model. If C equal to 7 means it goes to second model. And next one, here you see how many number of customers can be joined in that queue. Infinite number of customers can be joined in that queue under the queue discipline FIFO, first in first model. Like that, MM1 colon K bar FIFO means number of customers here restricted at certain number, at certain limit. So here Markovian arrival rate Poisson and Markovian service rate mu exponential distribution with one server, and finite number of people should be there. Finite number of people should be there to be served under the queue discipline FIFO, first in first out model. And similarly MMC, so first Markovian Poisson process and Markovian service time distribution follows exponential distribution, that is second M. And here see system number of servers are there, I mean more than one number of servers are there, and finite number of people to be served or finite number of customers to be served under the discipline of the queue FIFO, first in first out. So this is queue discipline. And next very important formula, that formula is called Little's formula, where we can bridge among waiting time in the system, waiting time in the queue, number of customers in the system and the number of customers in the queue. So Little's formula gives us the connection among these four important components. First you see LS equal to lambda divided by mu minus lambda. This lambda is arrival rate and this mu is service rate. So arrival rate divided by service rate minus arrival rate. This can be written by lambda into WS. So that is equal to LQ plus lambda divided by mu. So this also can be defined like this. And second point WS. WS equal to 1 divided by service rate minus arrival rate. That can be written WQ plus 1 divided by mu. That is equal to LS. LS is number of customers in the system divided by arrival rate. Arrival rate. That can be defined in some other way. And next LQ, number of customers in the queue equal to lambda square divided by mu minus lambda square. I mean arrival rate square divided by service rate, mean service time rate minus arrival rate. That can be written in another way, lambda into WQ. And next one WQ. Actually this is this is first formula, this is second formula, this is third formula, and you call this formula as fourth formula. This fourth formula is nothing but WQ. I mean waiting time in the queue. That waiting time in the queue can be defined as LQ divided by lambda. So if you know LQ, then by substituting lambda value, then we can find easily WQ formula. Otherwise, by just only having arrival rate and service rate, by having arrival rate and service time distribution, then we can find out what is the waiting time in the queue. And this row is very important component. This row is nothing but lambda divided by mu. Row value equal to lambda divided by mu. You observe this formula are very important. So using Little's formula, we can find if lambda and mu are given. Using Little's formula, we can find number of customers in the system, number of customers in the queue, and waiting time in the system, waiting time in the queue. So among this connection, I mean this strong connection among these components gives you the importance of Little's formula. First let us see one problem. This problem is given under first model. In a given MM1 queuing, you simply call it as MM1. In a given MM1 queuing system, the average arrivals is 4 customers per minute and row equal to 0.7. So here we are given 4 customers. The average arrivals is 4 customers per minute and row value is given, row value equal to 0.7. Now what is, these are all the sub questions we are asked to find out. Mean number of customers in the system, mean number of customers in the queue. Mean number of customers in the system means we have to find out LS. Mean number of customers in the queue, we have to find out LQ. Probability that the server is idle. For this case, we have to find out P0. There is one formula. When solving problem, we shall see. And mean waiting time WS in the system, and mean waiting time in the queue. That is, we have to find out WQ. So given model is MM1 infinity bar FIFO, and given mean arrival rate is lambda, that is equal to 4, and rho equal to 0.7. We know that rho equal to lambda divided by mu by Little's formula. By by basic notation, rho equal to lambda divided by mu. Simply substitute rho value here, then otherwise you take mu left hand side and take this rho to denominator of right hand side, then mu equal to lambda divided by rho. Now we have to find out service rate and arrival rate. Arrival pattern is given in the formula, and we have to find out service time distribution. To find service time distribution, from rho we are adjusting the components, adjusting the formula, and we can able to find out mu value. So rho equal to lambda divided by mu, then mu equal to lambda divided by rho. So that is equal to, already lambda is given as 4 and rho is given as 0.7. Substitute this value here, but therefore mean service rate, this has been taken as one fraction, then mu equal to 40 divided by 7. So we have found arrival pattern, this arrival rate lambda divided by 4 and service time distribution. I mean service time, simply you call it as service time. Service time distribution mu equal to 40 divided by 7. Now first we have to find out LS. LS equal to lambda divided by mu minus lambda. Substitute lambda value here and mu value here, lambda value here in this formula. Substituting lambda and mu values in this formula, then we can get 2.33. These are all based on number of persons. So number of person 2.33 is meaningless, as 2.33 can be written as written in terms of whole number 2, then 2 customers approximately. And next, mean number of customers in the queue. So mean number of customers in the queue as per the Little's formula, lambda square divided by mu minus lambda. So substitute lambda value here and mu value here, lambda value here. Actually I have taken lambda divided by mu outside, and lambda divided by mu is nothing but rho value, and this is nothing but LS value. Then substituting rho and LS here, I have found the value 1.6, that is approximately equal to 2. Otherwise you simply substitute lambda value and mu value, lambda value and mu value here directly, then also you can get the same result 1.631, that is approximately 2 customers. Sorry. And next, probability that the server is idle. Probability that the server is idle. To find out answer for this question, we have to use one formula. That formula is nothing but P naught equal to 1 minus lambda divided by mu. P naught equal to 1 minus lambda. Simply substitute lambda value and mu value, or lambda by mu equal to rho. Rho value already we are given 0.7, then 1 minus 0.7 equal to 0.3 is the time the server is idle. The server is idle means he is not serving to any people, he is simply sitting on that time. Okay, then what is the size of the time? Simply sitting time of the sitting size of the time, that is 0.3. And next, fourth one, mean waiting time of a customer in the system, that is WS. WS, by using Little's formula, WS can be calculated by using LS divided by lambda. Already we have found LS value. Simply substitute LS value. What is LS? Number of customers in the system. LS value you substitute here and lambda value you substitute here, then 0.58 minutes, because WS is waiting time, it is connected with time, so you have to note here minutes. Why should we note minutes? Because in our problem it is given that the arrival pattern is in terms of minutes only, so the unit is minutes. Time unit is here minutes, so you simply write it as minutes, 0.58 minutes. And next, mean waiting time of a customer in the queue. Mean waiting time of a customer in the queue is nothing but WQ. The WQ, by using Little's formula, LQ divided by lambda. Simply substitute LQ and the lambda value there, then 1.631 divided by 4, that is equal to 0.41 minutes. This is also mean waiting time. I mean that unit should be noted in terms of time only, that is why I have written 0.41 minutes. So this is the way to solve some problems using Little's formula. And next we shall see further problems, further beautiful problems in the next video lesson. Thank you.